In the late 1600s, a new way of describing motion took hold. Isaac Newton laid out simple rules that connected force, mass, and acceleration, and he backed them with a powerful idea. The same laws applied everywhere. Apples fell, cannonballs flew, and planets curved through space for the same basic reason. Nature started to look like a machine, not a mystery. Newton's laws did more than explain what people already saw. They turned the universe into something you could calculate. If you knew where an object was, how fast it moved, and what forces acted on it, the next moment followed from the last like a chain. The future was not guessed. It was derived. Predictions stopped being a hope and started to feel like a right. This was the clockwork promise. With perfect starting information, the path ahead was fixed. Any surprise came from missing data, not from nature making a choice. Randomness in this picture was a label for human limits, bad measurements, unknown pushes, hidden details. The laws themselves left no room for chance. In principle, everything that happened had to happen. In the early 1800s, a French mathematician named Pierre-Simon Laplace took that clockwork picture and pushed it to its limit. He treated the universe like a giant calculation. Every planet, every stone, every gust of air followed exact rules. If the rules stayed fixed, then the future never truly surprised anyone. It only looked surprising because people lacked the numbers. Laplace laid out a famous thought experiment that later became known as Laplace's demon. He imagined an intellect that knew the precise position and motion of every particle at one instant, and also knew the laws of nature perfectly. With that information, it calculated the entire future and reconstructed the entire past. Nothing remained uncertain. Randomness became a label for missing information. That move mattered, because it turned mechanics into a claim about reality itself. In this view, the universe did not merely behave predictably in practice, it behaved predictably in principle. Every coin toss, every storm, every heartbeat followed from earlier conditions like links in a chain. Freedom, chance, and accident started to look like human illusions. Determinism stopped sounding like math and started sounding like fate. By the mid-1800s, physics faced a new kind of problem. Heat engines powered industry, but no one fully understood why they wasted energy. Thermodynamics changed that. It tracked energy and introduced a blunt fact. Some processes always ran one way. Heat spread out, work degraded. This arrow looked like chance had entered the machine. If motion followed laws, why did large systems behave so predictably messy? The answer came when physicists treated matter as crowds of tiny moving parts. One scientist, Ludwig Boltzmann, pushed this idea hard. Instead of following every particle, he used statistics to describe the whole swarm. Temperature and pressure became averages. And probability became a tool, not a confession of magic. The gas did not obey dice. People simply could not track trillions of collisions, so they calculated likelihoods instead. That shift rewired what random meant in physics. A coin toss looked random, yet it still followed mechanics. The chaos came from hidden details, tiny pushes, air currents, exact angles. Statistical mechanics treated heat the same way. Irreversibility looked unavoidable because the most likely arrangements were the most spread out ones. So, probability entered the equations, but it usually pointed to ignorance, not a fundamental break in cause and effect. By the early 1900s, one stubborn problem kept refusing to fit the old picture. When light hit certain metals, electrons flew out. Turn the light down, and you expected fewer electrons, maybe slower ones. That seemed reasonable. But the experiments did not behave like that. Below a certain color of light, nothing happened at all. Above it, electrons came out immediately. Albert Einstein took that strange cut-off seriously. He treated light not as a smooth wave that spread energy continuously, but as tiny, separate packets of energy. One packet hit one electron. If the packet carried enough energy, the electron escaped. If it did not, no amount of dim light helped, because the energy did not add up smoothly over time. It arrived in lumps. This idea explained the photoelectric effect with a clean cause and effect, but it carried a bigger message. If light itself delivered energy in discrete pieces, then the old promise of perfect continuity started to crack. Nature looked less like a flowing stream and more like counted steps. It did not yet prove randomness, but it forced physics to accept limits that classical thinking never needed. By 1913, the old picture faced a stubborn problem. Atoms did not behave like tiny solar systems. Niels Bohr offered a fix that sounded almost like a rule book. Electrons did not orbit at any distance they pleased. They sat in specific allowed states, each with a set energy. The strange part mattered most. Atoms gave off light only when an electron moved between those states. That move did not look like a smooth slide. It looked like a jump. The atom stayed steady, then suddenly changed, and a precise color of light appeared. Bohr's model matched real spectra, so the idea stuck, even though it clashed with classical expectations. In classical physics, motion explained change step by step. Here, the key events happened without a continuous path anyone could track. Over the next decade, the allowed state idea spread beyond atoms. Old rules treated energy and motion as endlessly adjustable, but experiments kept pointing to only certain outcomes. Between 1913 and 1925, quantum theory grew into a new set of restrictions. Some values existed, others did not. Classical determinism still predicted smooth evolution from causes. Quantum results arrived in discrete steps, with the steps themselves left unexplained. In 1926, a young Austrian physicist, Erwin Schrödinger, replaced the idea of tidy particle paths with a new kind of rule. He wrote an equation that produced a wave function, a mathematical object that described what an electron could do, not what it definitely did. It spread out in space and time, it carried possibilities, and it forced a new question onto physics. What did a prediction even mean now? Max Born pushed the answer into sharper focus. He treated the wave function as a tool for probabilities. It did not point to a hidden, precise outcome waiting to be revealed. It gave chances for different outcomes. The math stopped promising certainty and started offering odds. That shift mattered. It meant that even with perfect equations, the result of a measurement came as a distribution, not a single guaranteed number. Then, in 1927, the uncertainty principle made the limit physical. It said that certain pairs of quantities, like position and momentum, could not both be pinned down exactly at the same time. This was not clumsy equipment or lack of skill. The act of defining one precisely washed out the other. The dream of total initial conditions cracked. Quantum theory did not just use probability as a shortcut, it built it into the rules. By 1935, quantum theory already worked frighteningly well. Yet for some of its creators, worked did not mean made sense. That year, Einstein joined forces with Boris Podolsky and Nathan Rosen, and they aimed straight at the weak point, the theory's claim that probabilities were not just practical, but fundamental. They argued that if quantum rules were the final word, physics had accepted an odd bargain. It predicted outcomes, but refused to describe reality in full. Their reasoning used a simple idea: measure one thing here, and you instantly learned something about a distant partner system without touching it. Quantum theory allowed pairs to be linked in a single shared description, later called entanglement. The EPR argument treated that link as a trap. If a measurement on one side let you predict a result on the other with certainty, then the distant system seemed to already have that value. Otherwise, the measurement appeared to reach across space. So EPR pushed a hard conclusion. Either quantum mechanics missed extra facts, hidden variables that fixed outcomes in a deeper, deterministic way, or it demanded a kind of influence that clashed with ordinary expectations about separation. They called the theory incomplete, not because it failed in calculations, but because it looked like it left parts of reality undefined until the last moment. The fight over randomness shifted. It no longer sounded philosophical, it sounded testable. In 1964, the debate stopped being only philosophical. A physicist named John Bell took the question that EPR had left hanging and turned it into arithmetic. If hidden causes really sat underneath quantum theory, Bell asked, then those causes had to obey two simple rules: locality, meaning no instant influence across space, and realism, meaning results existed before measurement. From those rules, he derived strict numerical limits. He called them inequalities. Bell's move mattered because it forced determinism to pay a price. In an entangled pair, each particle could carry a set of instructions, telling it what to do for every measurement choice. But if those instructions stayed local, the correlations between the two sides could only be so strong. Bell calculated exactly how strong. Quantum mechanics predicted correlations that could exceed that limit. One world had hidden variables and locality, the other had quantum randomness. They could not both be right. For the first time, the fight came down to an experiment anyone could score like a test, measure many entangled pairs, randomly change the measurement settings, compare the statistics. If the data stayed within Bell's inequality, then the randomness of quantum outcomes could still be blamed on unknown causes. If the inequality was violated, then no local hidden variable story could explain the results. Bell did not end the argument in 1964. He made it measurable. In the 1970s, Bell's idea stopped being a thought experiment and became a lab target. Physicists created pairs of particles that stayed linked, then measured them in different ways. If hidden, local instructions had guided the outcomes. The results had stayed inside Bell's limits. But the numbers repeatedly broke those limits. It looked like chance, yet many argued the tests still had escape routes. Those escape routes had names. Sometimes too many particles were missed, leaving doubt about whether the sample had been fair. Sometimes the measuring choices were set too early, leaving room for subtle signals. In the 1980s and 1990s, experiments tightened the screws. Faster switching, better detectors, longer distances. Each upgrade removed a classic excuse, and the violations kept appearing. By the 2010s, teams ran loophole-free Bell tests that combined high detection rates with genuinely separated choices and measurements. The results still violated Bell inequalities. The conclusion was blunt. Nature did not follow any theory that was both local and classically deterministic in the hidden variable way people had hoped. Something had to give. Either locality or that old dream of fixed outcomes waiting to be revealed. By the time the key Bell tests held up under tighter and tighter scrutiny, the fallback story grew harder to keep, that outcomes had been fixed all along, just hidden from view. Quantum events kept refusing a pre-written script, at least in any way that also respected locality. So the meaning of probability changed. It no longer stood for missing information. It stood for what nature actually delivered. That new stance carried a blunt consequence. Even with flawless instruments and perfect preparation, some results still arrived as genuine surprises. You could predict the pattern over many trials, but not the next single click. Randomness stopped being a temporary placeholder until better theory arrived. It became a physical resource, and once something became a resource, engineers looked for ways to capture it. In practice, that meant devices that turned quantum unpredictability into usable bits, then proved those bits had not come from a predictable machine. Certified random number generators did exactly that, producing randomness with mathematical tests tied to quantum behavior itself. Quantum cryptography leaned on the same idea. Any eavesdropping left detectable traces because measurement outcomes had not been preset. The old dream of perfect predictability ended as the new normal.